Okay guys, welcome back. So in the last video I talked as to how Newton's laws can be introduced. I defined those Newton's laws and explained how Newton's laws are applied in the day-to-day situations, daily occasions. So in this video, as I told you in the last video, I'll be focusing as to how Newton's laws are used in the concepts of rotational motion, right? Rotational motion. Now if you have studied, if you have watched the videos, and if you have not watched those videos, I invite you to watch the series of videos of mine on rotational motion. So if you have watched my videos, you would have noticed that most of the calculations, most of the equations, and most of the problems I used, or the solutions I used to explain those problems, in those solutions, problems and equations, I used the relationship or the analogous condition between the translational motion and rotational motion, right? So this is also another relationship in which Newton's laws play a simple but very important role in rotational motion. So now I will introduce the Newton's third law in a very brief manner, right? Because this is not about Newton's laws I am explaining. What I am explaining is the analogous condition or the similarity between translation motion and rotational motion using Newton's laws. So I'll briefly introduce the Newton's laws. If you are not watched the video on Newton's laws, I invite you to watch and see this video. So I'll briefly introduce the Newton's laws in order to explain you the relationship, right? So Newton's first law says, if an object is at rest, right, or if an object is moving at constant velocity, I'll take the velocity as v here, and here is 0, right? If an object is at rest, or if an object is moving at constant velocity, its motion or its path or its position or its behavior can only be changed by an external unbalanced force acting on that object. So if you put some external unbalanced force, say F here, F in this direction, and to this object F in this direction, its equilibrium or position or acceleration, everything will be harmed, and it will act in a new behavior, right? Its behavior will totally be changed. So what it actually means is that if an object is to be kept in motion, is to harm its behavior in motion, or for an object which is at rest to begin its motion, you need an external unbalanced force. Alright, so that's Newton's first law. Then Newton's second law explains, Newton's second law explains as to how the force varies with accelerations. If the mass of any object is a constant, if we are not adding mass or removing mass from an object, so the mass of this object is constant, so F is directly proportional to A. So Newton's second law says that the force applied on an object is directly proportional to the rate of change of its momentum, and the direction of force is in the direction of the rate of change of momentum. So if you have some force here on an object like this on the plane, right, which has mass m, and it is displaced by this force F, constant force. I will take a constant force so that the force is not varying with time. So t equals 0 here, and t equals t here, and the initial velocity I will take as u, and the final velocity v. We derive that v equals u plus at, and a equals v minus u by t. So F is equal to ma, right? F is equal to ma. So that's Newton's third law, the second law, right? So Newton's third law said explain that if you have an object like this, if you have some string like this, right, the tension applied by the string and the weight of this object are equal and opposite in direction. The action and reaction are opposite in direction but equal in magnitude. So T is in this direction, mg is downwards in this direction, but T is equal to mg. So if T is the action, mg is the reaction, and if mg is the action, T is the reaction. So So they are opposite in direction but equal in magnitude. So this is Newton's third law. Alright. Now how is these three laws analogous to the rotational motion? So that is the objective of this video. So alright. So you know that tau equals Fr, right? So this is the equation that I am going to use. This is the equation I am going to use to mention you about the relationship between translational motion and rotational motion using Newton's three laws of motion, right? So tau equals Fr, you know this equation. If you have not watched that video, I invite you to watch that video and come back here in my series of videos on rotational motion. So tau equals Fr here, right? So Newton's first law says for an object to keep in motion, for an object to harm its motion if it is going in at constant velocity, or for an object to start in motion if it is initially at rest, it needs an external unbalanced force. Now if you keep the radius of some constant, say if you are moving in some way, circle, right? If it is a circle, the radius will be constant at any point, right? If you are taking a circle like this, this radius here r will be equal to the radius here r, anywhere. Here r, this radius will be anywhere. The distance between the center and its circumference will be r. So in the videos on the rotational motion, I explained how there is an analogous condition between the angular motion, circular motion, and rotational motion. So if the radius is kept constant, tau is directly proportional to f. That means if the radius is 1, tau is equal to f. So what it actually means by this is that from the translational motion, you can say that for an object if you need to harm an object's motion if it is already in motion with some constant velocity, or to begin an object's motion if it is initially at rest, you need a force. Now if you multiply this force by some displacement, or if you multiply this force by the radius of this circle, or something sphere or something, what it actually means is that in rotational motion, for an object to get rid of its initial angular velocity, which is omega, or if it is initially at rest to start an angular velocity, right? Angular velocity, what it needs is an external unbalanced torque, right? This is not an external unbalanced force now, this is an external unbalanced torque. So if tau is equal to 0, the object will either move in constant angular velocity, or the object will be at rest, right? So if tau is not equal to 0, there will be a force. So from the Newton's first law, you can say that the object will either change its velocity from 0 to some value, or it will accelerate from some initial angular velocity to a final velocity. So that's the analogous condition between Newton's first law and rotational motion. So when you are considering Newton's second law, what it means, F equals ma, so you know tau equals Fr, so you can multiply both sides by r. So F r equals MAR, because F is equal to MA, Fr equals MA times R. So you know A equals R alpha. So Fr has been Fr is equal to tau here. So this is tau. So this is tau M. A is R alpha times another R here. So R times R is R squared. That multiplied by M is N R squared times alpha. So you know that mr squared is equal to I, which is the moment of inertia of that object. So tau is equal to I alpha. So this is another equation for equating tau. So what it actually means is that now F equals ma for an object which is moving in translational motion, which has an translational acceleration, right, or linear acceleration. So for an object which is moving in angular motion, it will have an angular acceleration which is alpha, and force and a torque of tau. So what it actually means is that if you are considering the analogous condition between Newton's second law and rotational motion, what it actually means is that from translational motion you can say the force acting on this object is directly proportional to its acceleration. So from rotational motion, what it means is that the torque acting on that object will be directly proportional to its angular acceleration, because the moment of inertia of an object is constant. So what it actually means, from translational motion, F is directly proportional to A, and from angular motion tau is directly proportional to alpha. So that's another condition in which Newton's laws play a critical role in building up or maintaining the relationship between translational motion and rotational motion. And Newton's third law, we don't have a special condition. So if you take in some a condition like this, right, a simple setup like this, so what it actually means is that there will be some force here, say mg, and there will be some force here mg, and there will be a friction force r. That's what you call a normal force or a contact force r here, right? So what it actually means, if an object is to be at equilibrium tau equals 0, so what it actually means, if tau is 0, Fr is 0, so R cannot be 0, so F is equal to 0. F is equal to 0 means that the total resultant force will be 0. So the total resultant force is 0 means there is no horizontal component in this direction. So what it actually means is that mg plus capital Mg is equal to R, or m plus capital M times g is equal to R. So what actually means is that even in translational motion, the total forces in one direction will be equal to the total force in other direction if the object is stationary or moving with constant velocity. So that is the analogous condition between the linear motion and rotational motion as expressed by the Newton's laws. So that's a very important video, I think, and if it is useful, so that's actually a link between translational motion and rotational motion. This is a link, right? One end is translational motion and the other end is rotational motion. It is bridged by Newton's laws. So that's a very simple video, but it is very, very important, very, very critical, right, to the importance of understanding the motions between linear motion, rotational motion, Newton's laws. All I expressed, I compacted all these things. I made it simply as possible and contracted all the things into one video. So I hope to see you in another video on another concept on mechanics, and see you then.